What would actually happen if two waves were to collide? A lot of time and research has actually been spent on answering this question, and it has led to the superposition principle, which states that when more than one wave occupies the same space at the same time, the displacements add at every point. It turns out that actually showing a collision between two waves is kind of difficult. It usually either requires a big setup or it's just hard to capture because the interaction happens so fast. The waves are usually traveling rather fast. But what I can do is I can simulate the interaction. Here I'm going to simulate what happens when two wave pulses collide. So think of these two shapes as just wave pulses that were created. If you want to think of it as, wiggles on a string, that works. They're traveling in opposite directions. Okay, and they're going to collide together. To do this simulation, all I'm really doing is plotting the mathematical formulas that represent each wave pulse. I'm just using plotting software to do that, and then I'm just going to advance each frame piece by piece. I'm just using plotting software to do that. And all I'm really doing is changing a time variable in my equations, and that will advance it frame by frame. Before I show you this, I want you to try to imagine what's going to happen when these two waveforms interact, when they actually collide. The interesting thing about waves is we've talked about how the thing that's actually traveling in a traveling wave is energy. So what does it look like when energy collides? Well, if you think of this as a string, and these are wave pulses on a string, then it would look like this. It's going to advance this one frame at a time. Okay, so you can see that they've started to interact, and there is a definite change now that they're interacting. The crazy thing about this, though, is it's just energy passing through the same point in space. So really, after the so-called collision, the energy just continues on in the same way it was going before, where this pulse is still moving to the left and that pulse is still moving to the right. I want to look at that interaction again, but this time what I'm going to do is I'm going to plot each pulse separately and the combination of the two pulses so that we can see what's happening with all three. So the solid blue line is going to be the actual combination. So think of that as what the rope would actually look like if these were two pulses on a rope. There's going to be a green dashed line that's representing this oddly curved shape pulse over here, and then there's a red dashed line that's representing the square wave. So think of that as that was what the original energy is doing at any of these points in time. And then the blue line is the combined actual result. So let's watch that interaction again. So before they overlap in space, nothing interesting happens. They're just moving along. Now they're just starting to interact. So see how the blue is the actual result, what a string would actually be doing. So hopefully you're seeing what's happening here. Really all you're doing is you're taking this green line and you're adding it to the red line to get the blue line. It's most obvious right here. You can see that the blue is just the sum of the red and green. This is what we call the superposition principle. So the energy really is just passing through as if nothing had happened, and it's still there after the interaction. So waves don't actually collide in the traditional sense. They overlap, they interfere with each other, so there is a sort of a visual net result, but in the end, energy doesn't stop the energy, it just continues on in the way it was moving. I want to look at this one more time, but in this situation, I've inverted the curved pulse. So let's watch what happens now that one of them is in the opposite, or the negative side. So you're seeing a different reaction here. The blue line, which is the actual total, is now being pulled down as these start to overlap. Okay, before, where the blue line was higher than this red line, it's now below. So the most obvious point is right here. So you can see that the blue line has been pulled down compared to what it was before. Really, we're just adding the two lines like we did before. It's just that one of those lines is now negative. So when you add a positive number and a negative number, you end up with less than you had before. Where in the previous situation, they were both positive, so you ended up with more than you had before. The overall interaction is the same as far as the end result. The energy just continues on as if nothing actually happened. It was just while they actually occupied the same space that they interfered with each other. The interaction of the two pulses that I just showed are examples of the superposition principle. When they overlap and when we have to add up their displacements, we call that interference. When the two have the same sign, so they added together to give a larger net displacement, that's what we call constructive interference. When they had opposite sign, so their addition resulted in less displacement, that's known as destructive interference. What would happen if you actually had two waves moving in opposite directions and those colliding and interfering with each other, overlapping in the same space? I'll use another plotting simulation to demonstrate this. Here I'm showing two waves traveling in opposite directions, and they're identical in wavelength, frequency, and speed. The only difference is the directions. Now I'm not showing their superposition here, I'm just giving you a chance to imagine two waves traveling in opposite directions. What do you think it would look like for the actual superposition? So imagine there was one string and you tried to have two waves going in opposite directions down that string. What would that actually look like? The nice thing about this program is I can show you. So the black here is what the string would actually be doing as these two identical waves are passing each other, moving in opposite directions. You can see that the string is waving, but is it traveling? Maybe it'll help if I fill in some color. All right, now I'm just filling in underneath the wave. So I'll go back to my question. Is this wave traveling? Well, how we always do it is you look at a point on the wave and you just follow it. So for this red one, clearly I'm moving, I'm traveling. For the total, the black here, I'm moving up and down, but this peak here is not moving. This is what we call a standing wave. There's definitely wave action, but it's not traveling. It's staying in one spot, so we call it, again, a standing wave. You get a standing wave by, as you can see here, having two identical waves traveling in opposite directions, but overlapping in the same space. So this is a result of their superposition. We just saw what happens when two identical waves are moving in opposite directions and they overlap. There was a moment when they perfectly overlap, And if we're adding up their displacements, because they have opposite signs, the total is right here in the middle. It's kind of hard to tell. It's this blue line right in the middle. In this situation, this is called perfect destructive interference, because you actually end up with zero displacement overall. Everything is perfectly canceling out everything else. There's another moment when they match up exactly. And now when they add together, you end up with twice what you had before, or twice as big as any single one. This would be a situation called perfect constructive interference. So they're perfectly adding together, so you get twice as much at every point. Now I say twice because these were identical waves. There's two more features of a standing wave that I want to point out. So as you watch the red standing wave here, you'll notice that there's actually points along the wave that aren't moving at all, like this one right here and this one right here. They're always in the same spot, where every other point on this red wave is moving up and down. The other feature I want to point out is that there's always a location for maximum displacement. These 2 points have special names. A node is a point of zero displacement at any time. So that point right there would represent a node. It's always zero displacement, meaning there's no motion. It's not moving anywhere. I can mark all those nodes on the standing wave like that. An antinode is a point of maximum displacement right there, and I'll mark all of those. Notice that this point down here is also an antinode because the wave peak is right there now, but it's a standing wave, so eventually it'll move back down and line up with that. So both top and bottom would be considered an antinode, as you can see here. So this is the basics of superposition, wave superposition. This leads to a lot of interesting and important phenomena in physics. Unfortunately, without mathematics, we really can't get into it much deeper than this. So I think we're going to just leave it at this point as far as our basic introduction. I'm going to switch topics now. This would be a good place to hit pause and take a break if you want to. We're going to move on for about another 15 minutes. I'm going to play a video for you, and it's going to seem a little strange why I'm showing you this video. I actually don't want you to focus on the video itself. I want you to focus on the sound coming from the video. That was probably nothing new for you. You've heard sounds like that before in your life. What I want to address is the fact that the sound of coming from the car horn seemed to change as the car was approaching, and then there was a noticeable significant change as it passed. That change in sound is due to the Doppler effect. The Doppler effect is a change in the perceived frequency of a wave due to the motion of the wave source, or the motion of the receiver of the wave. I mentioned in the previous video that for sound, the frequency of the wave is commonly referred to as the pitch. So you could say that the Doppler effect for sound is a change in the perceived pitch. I just gave you an audible demonstration of the Doppler effect with the car as it was driving by holding its horn. For a visual demonstration, I can't use sound. That's not something we can see. So I'm going to instead use a water wave. Think of this as somebody just dropped a pebble into a still pond. You can see the waves that emanated outward as a result. Now, if I were to have some sort of device in the middle here that just kept going up and down like a plunger, a mechanical plunger, then you could imagine that these circular water waves would just emanate outward indefinitely. Here I have a simulation of that. So again, this is like a little plunger going up and down with a very steady frequency. And that's resulting in emanating water waves with very well-defined wavelengths. The speed at which these waves travel actually depends on the water itself. It's the physical properties of the medium that define the wave speed for any wave, like sound or water in this case. So I'm going to pause that so I can show you the wavelength specifically would be the distance between two crests. So think of each one of these black circular lines as a wave crest. Now I want to consider what would happen if the source continued at a steady regular frequency, but the source itself started to move. I'm going to have it travel to the right. How would that affect the waves? I can simulate that easy enough. It's going to look like this. You notice there's a definite difference in the characteristics. Let's look at that. If we look behind the source, as the waves are going away from the receding source, the wavelength is noticeably longer than the wavelength in front, or where the source is approaching. So the reason why that is the waves themselves are still emanating at the same frequency. So the source is trying to create a constant wavelength. But when one wave comes out, the next wave is actually closer to that wave in the front because the source itself is chasing that wave that was emitted. So the wavelength decreases in front. In the back, when one wave is emitted, the source is running away from that wave, so the next time a new wave comes out, it's further away than it would have otherwise been. So we end up with a longer wavelength in the back. If I compare the original wavelength of a source at rest, that's my original wavelength from my previous figure. So you can see that the wavelength in the rear is actually noticeably longer, and the wavelength in the front is noticeably shorter compared to the original source wavelength. If you remember, wave speed is equal to wavelength times frequency. Wave speed should be the same for the front and the back, because it's all the same water, and the wave speed is dependent on the water itself, not on the source. So if both front and back have the same wave speed, we can discuss their frequencies by doing a little bit of algebra. So really, the frequency is just dependent on the wavelength. And we can see the comparative wavelengths here. So what we can say then is that the frequency in back is less than the frequency at rest. That's because in the back, the wavelength is longer, and wavelength is in the denominator, so that gives you a shorter or smaller frequency. In the front, that would mean that the frequency is more than the frequency at rest. And this actually is an easy enough example to show in real life. Here is a swan swimming through water. If you look at the ripples coming off the swan in the front, you can see that they're definitely closer together, and as they go around the swan here, they start to spread out. Now, this picture doesn't show you what it looks like in the back, most likely because there's probably a lot of turbulence, so it isn't obvious in that case. But you can clearly see how the waves are piling up in the front. So this is something real, the Doppler effect. This would be like a Doppler effect for water waves. It actually works for any type of wave. Let's imagine that instead of water, this is a stereo speaker, and these are sound waves that are emanating from the speaker. If the source is at rest, then all sides have this nice, well-defined wavelength, or in other words, frequency. So the observers here are receiving the same wavelength or the same frequency. They're hearing the same sound. Now what happens if my source starts to move, and I'll have it travel in the same direction to the right. Okay, that same effect happens as our water wave. My observer in the direction that the source is heading is receiving waves that are of shorter wavelength. The observer that sees the source receding or moving away from it is receiving longer wavelengths. The wave speed for sound is determined by the air, and the air should be the same for both of these observers, so the speed of the wave will be the same. That allows us to directly compare frequency and wavelength. So we can say that for the observer in the back here, the frequency observed from a receding source is lower than the source frequency. And then in the front, we can say that the frequency observed from an approaching source is higher than the source frequency. And that's because of the wavelengths that you can see here. So smaller wavelength is bigger frequency. That's because the wave speeds are the same. For sound, I've said that frequency is often referred to as pitch. So what we can say then is that the pitch observed from a receding source is lower than the source pitch. The pitch observed from an approaching source is higher than the source pitch. And what's interesting is this picture visually was just an effect of the speed that I gave the source. You could imagine that if I slowed down the source or sped up the source, it would also change the relative wavelengths. So I can state that the faster the source moves, the more the pitch is shifted, because you can imagine in front these would pile up even closer. All right, well, let's watch that video again now with this in mind and see if it's obvious. Does the pitch go higher for an approaching source and then lower for a receding source? Right now it's approaching. You can hear it go up. And now that it's past, the pitch goes low. It's that deeper sound. So it does work. The Doppler effect audibly works pretty good. I should mention that the Doppler effect also applies if it's the receiver that's moving. So in this case, I have a stationary source, but I have an observer who's approaching that source. From the observer's perspective, they're running into the wave crests at a faster rate, so the frequency that they observe goes up. Or in other words, the observed wavelength from their perspective went down. I want to show you some practical applications for the Doppler effect, and we're seeing one here. This is just a screenshot of a weather report from a TV station. If you've ever watched one of those weather reports, they often say something about a Doppler radar, or they show something that looks like this. The Doppler radar is just a special radar that uses the Doppler effect. They're measuring the shift in frequencies due to moving sources. Now, exactly how the Doppler radar works, I'm not going to get into it, but the underlying effect is the Doppler effect. Just as a reminder, the Doppler effect is a change in the perceived frequency. And I want to emphasize that word perceived. We observe the frequency as being different, but it's not actually different in terms of what's coming from the source. So it's a perception that we have because of the motion. If either the source or the receiver is receding, you end up with a longer wavelength, which is the same thing as saying a lower frequency. If either the source or the observer is approaching, you get a smaller wavelength, which is the same thing as saying a higher frequency. This little cartoon of a police car actually fits in with my next example for practical application. If you've ever been driving and you see a police officer pointing one of these at you, you probably know that the officer is measuring your speed. This is commonly referred to as a radar gun. How this works is it sends out a signal of light. It's not visible, we can't actually see it. That light is just a wave, so it emanates away from the gun. It hits your vehicle and reflects off of that. The reflected light returns to the receiver, and the device knows its original frequency. It can measure the frequency of the return signal, and it can compare the shift, and from that you can determine the actual speed of the object. Now, to show you that mathematically requires a lot of algebra, so we won't do that, but the basic concept is still there. It's just the Doppler effect. In this case, it's using it for light. So let's look at an example of visible light. We'll talk more about visible light in chapter 26. Visible light, you may have heard from other science classes, it's just a combination of all the colors. So it goes from red up to violet. And I want to focus on red and blue light right now. So red and blue light are both just waves. The only difference, maybe you could see from the animation, blue had a much higher frequency. As it was being traced out, it was wiggling a lot more in comparison to the red. Now the other way to think about that, and it's pretty easy to see here, is red has a longer wavelength than blue. We can actually compare those numerically. The wavelength of red is 700 nanometers. A nanometer is a 1/1000th of a meter. So these are really small. Blue, by comparison, is 400 nanometers. So it's noticeably shorter. These are both really small numbers, but blue has a shorter wavelength, or in other words, a higher frequency. I can say it has a higher frequency in relation to the wavelength because blue and red are both traveling at the same speed. Because these are both waves, they should observe the Doppler effect. We can visualize this with the same simulation as before. Instead of water waves or sound waves, this time imagine light waves. The source is just a light bulb. Light waves are emanating out, and on all sides they have the same properties, same wavelength, same frequency. So if I place two observers there, they're going to observe the same light. Now if I give the light bulb some motion, we'll use the same motion as before. It's the same effect. So visually, the observer for the approaching source is seeing light waves that have smaller wavelengths. In the back, where the source is receding, the observer perceives a longer wavelength. So we're going to state that the wavelength observed for a receding source is more than the source wavelength. Also, the wavelength observed for an approaching source is less than the source wavelength. In real life, the shift in wavelength is tiny. It's really, really small. But what we can say is that if it's now less than it was, the light in front for the approaching source has shifted very slightly to the blue end of visible light. The light in back for the receding source has shifted very slightly to the red end of visible light. So red had the longer wavelength, blue had the shorter wavelength. In general, we say that light from a receding source is red shifted. Light from an approaching source is blue shifted. I need to emphasize that the light does not appear red or blue. We don't say that the light has become red or blue. It's just slightly shifted that way. Visibly, human beings would never notice the shift. We would see the exact same light, whether the object was at rest or approaching. To even measure this, we need highly sensitive equipment known as spectrometers. So they are able to distinguish, but our human eyes would not know the difference. So it doesn't look red or blue. As a practical example, I'm going to show some astrophysics. So here I have an animation of a star and a planet. The planet is going around the star. Now it might look a little funny because we normally think that the planet revolves around a motionless star. But that's not actually how it works. We've talked a little bit about center of mass. When you have two objects like this, the center of mass won't be exactly in the star center, it'll be slightly shifted out towards the planet. So what actually happens in space is that the star, both the star and the planet, orbit their center of mass. So that's what this is trying to show. Right here in the center would be the center of mass between the two of them. Both the star and the planet orbit that center of mass. The end result, as far as our current discussion, is that the star actually wobbles from our perspective. Okay, if we're over here watching this and we're lucky enough to have this be edge on for us, then from our perspective, the star is actually going back and forth. But what it's really doing, it's actually going away from us at some point and then towards us at another point. So if you watch the coloring shift down here, as it's approaching, we see a blue shift, and then when it starts to recede, we see a red shift. And again, it's a little misleading. It doesn't actually mean it looks red or blue. It's just a slight shift towards smaller wavelength and longer wavelength. So if we're an observer over here, we call this the Doppler shift due to stellar wobble. When the star approaches, slight shift to the blue. When it recedes, slight shift to the red. Again, these pictures are often misleading because it makes it seem like we're seeing blue light then red light, but it doesn't work that way. The stars aren't blinking in terms of color. It's a very, very fine shift that only special equipment can measure. But it works, and it's actually responsible for finding hundreds of planets around stars other than our own sun. So we call these extrasolar planets. Another cool application is shown in this picture. Now, it's not really shown in the picture. Let me explain. This is a Hubble Deep Field picture. You've probably heard of the Hubble Space Telescope. At one point, it pointed at this very, very dark spot in the sky that everybody thought was just empty space, as far as what we could tell with the technology before the Hubble telescope. The Hubble, after peering at that spot for many days, was able to resolve pictures like this, and it really blew everybody away because it showed that space is really vast. There's tons of stuff out there. But what I want to mention in terms of our current topic is that if we measure the shift, either red or blue, of all of these objects, it turns out that they're all red shifted. That means that they're all receding away from us. I should warn you, that does not mean that we are the center of the universe and everything is moving away from us. It's a lot more complicated than that. And if you want an explanation, you should consider taking an astronomy class. All right, we're going to end it there. That was our discussion of wave superposition and the Doppler effect.